Hello, hello! Welcome back to the worst YouTube channel on Earth. Today we're going to be going over our last concept, which is spheres and tori. So before we get started, I'm going to explain a concept that's going to help us out later in the video, and that concept is frustrums. A frustrum is basically what you get when you take a three-dimensional object and you slice it with a plane parallel to the base. The frustrum is the part of the object below the plane. Today I'll only be explaining the frustrums of cones, specifically their lateral area, because this information will be very helpful later on when I explain the formulas of spheres. Now I'll draw the frustrum down below and show what it would be like if the cone was full. Now we already know that cones have a radius, a slant height, and a height. Frustrums, however, have two radii, one on the top base and one on the bottom base. It also has a height and a slant height, which is the height of the lateral surface between the two bases. We'll call the top part of the cone the apex. So, first, I'll use similar right triangles and proportions in order to find the lengths of some of the dimensions. So here I find that R2 times the slant height of the apex is equal to R1 times the slant height of the apex plus R1 times the slant height of the frustrum. The lateral area of a frustrum would be equal to the lateral area of the whole cone minus the lateral area of the apex. We also know that the lateral area of a cone is pi times R times slant height. So we can just substitute in those numbers and distribute the pi out. We get pi times R2LA plus R2LF minus R1LA. Now, we already figured out before that R2LA is equal to R1LA plus R1LF. So we can substitute that in, the R1LAs cancel out, and we're left with pi times R1LF plus R2LF. You can factor out the LF and get pi times LF times R1 plus R2, or pi times the slant height of the frustrum times the sum of the two radii. So let's talk about spheres. If you remember from my locus video, then you know that you can think of a sphere as all the points equidistant from a center point in 3D space. However, another way to think of a sphere is to take a circle, draw a diameter through it, and rotate the circle around the diameter. And what you end up with is a sphere, which is the set of all the circles that have the same diameter. So here's a side view. Let's say the dot is the diameter, and you can see that we're rotating the circle around the diameter. And it might look like a circle from this perspective, but you have to remember that each of these lines is actually a circle, so it's curved in your direction. Now I'm going to explain the formulas for the volume and surface area of the sphere. This is going to be a rather long explanation, so if you want to skip ahead, I'll have a few links on the screen that you can click and they'll take you right to the formulas. For the rest of you who want to learn how to figure this out, then just stick around. So above I showed you how you can think of a sphere as a circle rotated about a diameter. Well, what if instead of a circle it was a regular hexagon, or a regular octagon, or a regular decagon, and so on? So as you increase the number of sides, you can see that it gets closer and closer to looking like a circle. And this is what some Greek mathematicians like Archimedes used to figure out the volume and surface area of a sphere. So let's start with the surface area of a sphere. So let's say that we have a regular octagon rotated around its diameter, so we kind of form a regular octagon ball. And you can see that it's basically just the octagon rotated around a diameter. And if we separate it, we can see that it's actually formed of two cones and two frustrums, like we talked about earlier. This means that we can find the surface area of the ball and approximate the surface area of a sphere, because as we know, as the ball gets more and more sides, then it becomes more and more like a circle. So to start, I'll just draw some auxiliary segments that will help us later on, and I'll also draw in this right triangle that's inscribed in the semicircle. So I'll also draw these other two auxiliary segments that form a few other right triangles. I'll label these distances across the diameter A1, A1, A2, A2, A1, and A1. And we know that the A1 segments are congruent to each other and the A2 segments are congruent to each other because of congruent triangles. I'll also label the radii of the cone R1 and the other radii of the frustrum R2. So I'll label the big right triangle ABC. We should also note that all of the right triangles are similar because their inscribed angles intercept a 45-degree arc. So the surface area of the octagonal ball would just basically be 2 times the lateral area of the cone plus 2 times the lateral area of the frustrums. So we already know the lateral area of a cone is pi times r times l, and the lateral area of a frustrum is pi times the slant height of the frustrum times the sum of the two radii. So we can just plug in all the numbers, r1 for the radius of the cone, S for the slant height of the cone, S for the slant height of the frustrum, and R1 and R2 for the radii of the frustrum. And here I'm shading in the cones to make them more distinguishable from the frustrums. If we multiply everything together and factor out the 2 pi, then what we end up with is 2 pi times r1s plus r1s plus r2s. Now, we know that all of the right triangles are similar, so we're going to use proportions in order to help simplify this equation even further. a1 over r1 equals a2 over r2 equals a1 over r1 again equals bc over ac. And we also know that bc is the same as the side length, so we can just substitute bc with s. Now I'll cross multiply all of them into the ratio of s over ac, in order to get that r1s equals a1ac, r2s equals a2ac, and r1s equals a1ac. Now, the addition property lets us add r1s plus r1s plus r2s and make it equal to a1ac plus a1ac plus a2ac. So now we know that r1s plus r1s plus r2s is equal to a1ac plus a1ac plus a2ac. And you can see that up there we already have r1s plus r1s plus r2s, so we can substitute that in for its equal, factor out the AC, and we're left with 2 pi AC times A1 plus A1 plus A2. And if you look at the octagon, then A1 plus A1 plus A2 is equal to the radius of the octagon. So we can substitute A1 plus A1 plus A2 for the radius, and we end up with 2 pi r times AC. Now, here's something else interesting. So here's a regular decagon. I've drawn the same right triangle in with the hypotenuse as the diameter and one endpoint of the longer leg being the consecutive vertex. And although they're not the same size, you know that the distance between the legs would be smaller if they were the same size, because the angle measure has gotten smaller since there are more sides on the regular decagon. And if we increase the number of sides, and therefore decrease the angle and the distance between the leg and the hypotenuse, you can see that it holds true. So if we continue on, we eventually get to a circle where there's an infinite number of sides and the diameter and the hypotenuse essentially become the same line. So AC, the leg, will become equal to AB, the diameter. And this means that AC will be equal to 2r. So if we substitute in 2r for AC, we get 4 pi r squared, which is indeed the surface area of a sphere. So now let's go into the volume of spheres. So let's say that we have a sphere, but it's actually a polyhedron with lots of faces that are tiny triangles. If you were to connect each of these triangles to the center, it would form a triangular pyramid. And we know that the volume of a pyramid is 1/3 times base times height, so the volume of the circle would be 1/3 base height plus 1/3 base height, and so on. Now, we can factor out the 1/3 in height to get 1/3 height times b plus b plus b plus b, and so on. The sum of all the base areas would just be the sum of all the triangle areas, and the sum of all the triangle areas is equal to the surface area of a sphere, and we know that the surface area of a sphere is 4 pi r squared. So we could substitute that in. We also know that if it was a sphere, then the height of the pyramid would just be the radius. So we can substitute that in for the height as well. So the height would turn into r, the sum of the bases would turn into 4 pi r squared, and if we simplify, we get that the volume of a sphere is 4/3 pi r cubed, which indeed it is. So let's go into tori. Tori are pretty easy. So tori are basically just donuts. And a more mathematical way to think about it is, you have a center, there's a circle, and the radius of the circle is capital R. And each point on the circle is the center of a smaller circle that is coplanar with the center of the torus, and it has a radius of lowercase r. So I'll draw a cross-section below because the above picture might be a little confusing. Since the torus is just composed of circles, its surface area would basically just be the circumference of each of the circles on the tube times the number of circles. So the circumference of each of the outer circles is equal to 2 pi lowercase r, and the number of circles is equal to the number of points on the big circle, which is 2 pi uppercase r. So if we multiply that all together, we get 4 pi squared uppercase r times lowercase r. And in the same spirit, the volume of the torus would basically be the sum of all the areas of all the circles. So that would be pi lowercase r squared times the number of circles, which is 2 pi uppercase r, and that's 2 pi squared uppercase r times lowercase r squared. So that was spheres and torus. That was a pretty long video, and I hope I did not help.